Alright, so this is a tutorial on how to do AC mesh equations in Circuit Tutor. I'll be doing a mastery level problem in hopes that this will address any issues that you could run into on an easier level. So we always start with our current constraint equations, and we can see that there is one current supply, and that current supply has two meshes running through it. So we're going to say that I1S is going to be equal to the difference between currents 1 and current 2, and we can see that current 2 is running in the same direction as the arrow on the supply, so that is the positive current, and then we just assign that to the definition of I1S. Then we look and we see that there are no other current supplies, but there is a control variable, Vx, which is given by the voltage across the J1 impedance, and we can say that the J1 impedance has one current running through it, so we will pick the appropriate term for that. And we can see that the current is running into the negative side of the impedance, so we put a negative sign in front of the current, check that equation, and it's correct. So we are also seeking a branch voltage, and the branch voltage that we're looking for is the voltage across the current supply. Now, there is no resistance associated with current supplies, which is generally how we find output voltage. So what we can say, however, is that these two impedances, when combined in series, would actually be in parallel with the output voltage. So what we're going to do is we're going to say that V out is equal to the sum of both of these terms, and if V out were placed onto these combined impedances, we would see that current 1 is running through the negative end of these. So once we fill in all of the appropriate fields, we put a negative sign in front of V out, because current 1 is running into the negative side of, or the negative end of these two impedances. You could put a negative in front of both of the terms on the right-hand side, but this was fewer keystrokes to do it this way. So we check this equation, it's correct, and it looks like now we have all of our equations. So we should be able to move on to solving. You can see here that Circuit Tutor is bugging a little bit, but it is now writing itself. So we're going to need MATLAB for much of the coming sections of this. I write the equations in the order that they appear on the screen. So there is a -1 coefficient, a +1 coefficient, and 5, 0. The first equation is pretty straightforward. The second equation, I'm going to move into MATLAB. So I'm going to say that I1 of equation 2, and that's just how I name my variables. You can name them whatever you want. And it's defined as, and I'm going to sum all of the coefficients for I1. And then you can just copy and paste these right into Circuit Tutor. Obviously these ones are fairly simple. You probably could have done them in your head or on a piece of paper, but there are some that are a little more complicated, so I just get in the habit of using MATLAB anyway. So current 2 of equation 2 is given by, and then we're going to sum all of the coefficients for this variable. Then we can copy and paste this solution. And then this particular variable, there's only one coefficient, and the solution for that equation is 0. Then on this last equation, we have to add or subtract one of the variables and move it over to the other side. So I decided to add the right-hand side to the left-hand side. Now it looks like we are asked to put it into a matrix. Conveniently, you can just hit copy from the equations that you just simplified, and Circuit Tutor will put it into a matrix for you. Now we have to solve that matrix. This we're going to use MATLAB for. If you don't recall the syntax for entering a matrix and a matrix for equations and solutions, you can see it on screen right now. The important thing is that you move from left to right, top to bottom. In between each new term, you put a space, and to move to the next row, you put a semicolon. So you can see that I've been doing that. There are 3 elements in each row, a space between each element, and then at the end of that row I put a semicolon. when you get to the end of this sentence, you actually just put a bracket. You don't need a semicolon at the very end, but then I did put one after the end bracket to suppress it because I don't need to print out M. Now for the solutions, meaning the matrix with the solutions to the equations, we need to convert this polar coordinate to Cartesian because MATLAB works in Cartesian. So you can see on screen the syntax for that. We're going to assign this polar coordinate 5, 0 to the variables x1, y1, which follow the form a plus bi, meaning that it would be x1 plus y1 times I. And you can see that now I have taken this polar coordinate and moved it into a Cartesian form and stored that as solution 1. Another important thing to note is that MATLAB works in radians, not degrees. So every time that you input a degreed value, you're going to have to multiply by pi over 180. So now we can see that the B matrix is given by these values, and if you have a good eye, you'll see that I made a slight error in naming one of my variables. So this is just the error message I got. Now I fixed it so the proper variables for the solutions are displayed, and now we are properly entering the solutions to our equation matrix. So the final answer matrix is going to be given by the inverse of the equation matrix times the solution matrix. And I always just store that as FIN for final. And these are all the solutions. So the first element is I1, the second is I2, and the last is IX, which we don't need. And all we're going to do is, now that these are in Cartesian, we're going to move them over to polar so that we can put them into Circuit Tutor. And the syntax for this will be given pretty soon. So right here we start and we're going to say that variables x1 and y1, and we're going to use the function cart to pol, and that just moves Cartesian to polar. So all you have to do is tell it that we're going to take the real and imaginary components of any particular variable. In this case, it's going to be the first element in our matrix final, or fin, and I've copied and pasted that for the second element. So we have I1 and I2 respectively stored as x1, y1, and x2, y2. Now, again, we need to convert that into polar, or excuse me, they are already converted to polar, but we need to print them out. So the radii are stored in the y variables, and the angles are stored in the x variables. So the radii we can just print out, but the angles we have to multiply by pi and divide by 180. Excuse me, we have to multiply by 180 and divide by pi because they are currently in radian form, or they're stored in radian form, and we need them to display in degree form. So once you do that, as you can see on screen, you can just copy and paste that right into Circuit Tutor. I'm going to do the same procedure for x2 and y2. And as you can see, they are all in there. Again, using the same procedure for both of them, we're going to check the answers. It says that we did it correctly. And now we need to find the sought value of this circuit. So for V out, we're going to go back into MATLAB, and we're going to use the values from our final matrix, because anytime we have to do a calculation, we have to use Cartesian for MATLAB. So I'm going to say that V out is, and then I'm just going to use fine of 1 for any time that I1 appears, and the rest of the equation will be input exactly as appears. And we can go ahead and suppress that because this will be given to us in Cartesian form. We again have to convert it to polar form, and you probably recall the syntax for that. I'm going to store the points as xf and yf just for x final and y final, but of course you can choose whatever you want. And then cart to pol, the real and imaginary components of V out. We can still suppress that, and then we're going to say that the radius for our V out is going to be given by YF, and then the angle for our V out is going to be given by XF times 180 divided by pi. Don't listen to me, you can see me doing it correctly on the screen. And then both of these will be given, and we can copy and paste them into Circuit Tutor. It's really quite lovely that Circuit Tutor takes copy and paste from MATLAB. And then this should give us the correct answer. Woohoo! All right. So the last step is to move from the frequency domain to the time domain. So the radius of the frequency domain becomes the amplitude of the time domain. And then the angle of the frequency domain becomes the lead or lag of the time domain. And it tells us that the frequency is 80 kilohertz. Now, in the time domain, we actually need angular frequency, not normal frequency. So the formula for that is that angular frequency equals 2 pi frequency. So you can see me making this calculation in MATLAB. We're going to take 80 kilohertz times 2 times pi. That gives us the frequency that we need. Even though there's an exponent on here, Circuit Tutor still accepts it. So you can, again, just copy and paste it, submit it, and all the answers are correct. So awesome, we don't need an explanation, and good luck.